G'day, it's Brezzo here, back at the lathe, and welcome back to part 2 of the pull gear, that is the reverse engineering of. In the last episode I got to the stage where I had finished the bottom casting of the pull gear, which included the 3-step pulleys with the poly V grooves in them, and I made a complete hash of this. I tore out huge sections of the casting as I was trying to cut and machine the grooves for the poly V belt. And as I wound up this last episode, I said I was going to try and track down a piece of 6061 alloy to replace this casting. And I tried and failed to find a piece the right size. The only piece I could find was a seller who had a piece 200 millimeters diameter. It was the correct length. But I thought about it and I just thought, oh, it's going to be turning all of that metal into swarf. It didn't seem right. So what I've decided to do is just to machine off these 3-step pulley sections and replace that with a smaller piece of 6061. So I can get, in fact I've ordered a piece that will do that job, and it's going to mean having to attach this replacement machine section to this large disc here, and there's enough metal there to be able to put, say, 6 socket head screws on the inside to rigidly mount that in place. I'll also use Loctite just to ensure that nothing ever gets loose on that. So it's a lot of work, but I didn't fancy redoing the casting and possibly having the same problem happen again. So I'm going to go ahead and machine all this off, and we'll make the new part, get that fitted, and then we can keep going with making the rest of the parts. Alrighty, well, that may be a bit sad to have to do that, but it's the only solution I can find that's not going to waste a lot of material. One of the next jobs I need to do here is to drill 6 holes around this circumference to attach the ring gear to the casting for the step pulley. And this is the casting that I just machined the back off, and I've got this dialed in a 4-jaw chuck ready to go on, so that after I've drilled my set of 6 holes here and I have the indexing attachment and the drilling attachment for my lathe set up, I can just swap out the chuck and drill all of the holes exactly the same setting. So I'm going to get my drilling attachment set up, and I'll drill the 6 holes, and they're going to be countersunk for socket head screws. Well, there's the 6 holes around the ring gear. These will be later drilled clearance for the screws that I'll be using, and I'll countersink these deeply enough so the heads sit just below the surface. So what I need to do now is to swap out the faceplate for the 4-jaw chuck with the casting for the lower pulley section and drill the identical pattern of holes in it. And I've locked my cross-slide in position, so as long as I use the same number of divisions I should get perfectly matching holes. At least that's the plan. Well, here's the assembly. Now, do you want the good news or the bad news? Well, the bad news is that there is no good news. Firstly, I have misaligned one of the drilled holes. All of the other 5 screws went in fine. The drilled hole in the casting underneath here does not line up with the drilled hole in the ring gear. How did that happen? I have no idea. I can only think that I miscounted when I was indexing around for that one hole. So that in itself means that this casting, to me anyway, is scrap and I can't use it. But the more badder news was that when I checked the concentricity of the ring gear in reference to the aluminium casting, it was out by nearly 0.8 of a millimetre. Once again, I have no explanation as to why that happened, but that means that this part is unusable. Because I had machined the outer circumference of this exactly the size, and the bore on the inside here was also exactly the size, so that with that out of alignment with the ring gear, it means that it's scrap. So that means that I have to start again. So what I've done is I made a new casting for the lower section of the pulley. I machined a shoulder here, which is the same diameter as the inside of the ring gear. So I was able to put the ring gear over that shoulder, and then I spotted through all 6 holes, drilled and tapped, so I know that those 6 holes line up with the ring gear. I've also left this outer diameter oversized by about a millimetre. And all of the other dimensions on this partly machined casting are also oversized. So when I put the ring gear back on, I will set that up in the 4-jaw chuck and dial in the ring gear, and all of the other features are going to be machined from that ring gear reference. Now, it should have been obvious that that's what you do from the get-go, but I didn't do it. I've also managed to track down a piece of alloy which I can use to make the step pulley section. That means I'm going to have to fabricate the entire assembly by once again drilling 6 holes and bolting this down to this casting from the inside, which I can do. That's going to work. But it's less than ideal. It means that you don't have the integrity of a complete casting, but given the loads that this thing is going to work under, I think it's going to be okay. So it's just one of those things. It's like 1 step forward, 2 steps backwards. And I'm angry with myself. I should have been more careful. I should have thought it through more. And like I say, I've got no excuse for what happened there. That's a complete train wreck. So what do you do? Well, like they say, when the going gets tough, the losers go and have a beer and drown their sorrows. Right, let's go and operate some heavy machinery. Well, here we are back on the lathe, and I must say after that last setback I felt a bit tired and emotional. But I've reset and got the new assembly dialed in on the 4-jaw chuck. So this is the ring gear at the back here, and I've set that to be running as accurately as I can get it. I've also machined this flat face of the casting to be its correct dimension, and I machined the outer diameter of the casting to be almost the correct dimension. I didn't worry about bringing it down exactly the same size as the ring gear. There's no need. I've also bored out the bearing recess close to its finished size, and I've machined a secondary recess here which is going to allow me to locate this piece of stock. So this is all oversized at the moment, and once I drill through my 6 screw holes, I can machine this to a finished spigot dimension, fit it inside that recess, transfer through the holes and drill and tap everything, and I'm going to torque that down with 6 M5 screws, and I'll also Loctite it as well, just to be as sure as I can that nothing's going to move later. When all of that's done, I can finish machine the step pulley section. So let's go ahead and get these 6 holes drilled. Okay, well, this part can come out now, and I'm going to work on getting this prepped by machining this edge down to fit that recess, and then we can marry the 2 parts together. Well, that's good enough for me. So I'm going to spot these holes through now and tap the threaded holes in the alloy section, the new stock. And when that's all bolted down hard, I can go ahead and finish off the lower section. There's still some work to be done in here too. There needs to be a recess cut, and we need to bore out precisely for the bearing and the shaft. But you know what? Things are looking up. It's not such a disaster after all. So as you can see here, I've torqued down these cap head screws, and they're locking that piece of alloy stock to the back of the base casting. And because all of this is oversized, I can go ahead now and grip this in the 4-jaw chuck and dial in the ring gear and make sure that's running accurately. I've got some copper shim around the jaws of the 4-jaw so I don't damage the teeth on the inside of the ring gear. So let's go ahead and get this all mounted and running true, and then we'll just have a quick look at some of that machining. Don't know if you can see that, but this edge of the ring gear is not actually truly circular, which is surprising. It's sort of running oddly. It seems to have 2 high spots, 2 low spots. I'll sort of dial it in, get it the average that I can. Like I say, it's a bit awkward because it's not consistently running out. Anyway, I've got it set at an average, so that's about the best I can do. Anyway, we're going to go ahead and get this all machined up here now. I'm going to use this as a temporary center so that when I start machining the outside of this billet I can keep some tailstock pressure on this part. And the bearing looks like it's the right sort of fit. I won't press that in just in case I can't get it out again, but I'm happy with that. So it's got another bore to finish off inside here, and then we can start shaping the outside. Alrighty, that's step 2, so I've got 1 to go, and then the grooves. Okay, what I've got here is a high-speed steel tool. It's ground much like a threading tool, except the included angle here is 40 degrees, which matches the Poly V belt. And what I need to be able to do is to cut 3 grooves in each one of these diameters, and the last time I just plunged the tool straight in, and of course that led to disaster. What I've done is I've set my compound slide round to half the flank angle, that's 20 degrees off 90 degrees across the lathe. I have set my tool so it's parallel to this face here, and I have offset the tool from this corner of the stock, this corner of the pulley face. And all I could do there was just eyeball it. So I've used a steel rule, I placed that against the shoulder, brought the tool back until I thought the corner was against the edge of the steel rule. Now, I did watch a video by Joe Piezinski who showed how to offset angular tools from edges and faces and so on, and it was brilliant, but I forgot it all. And in any case, it doesn't really matter. What's important is that the 3 grooves are equally spaced. The offset from this edge is less important. The belt is not as wide as that face, so even if I get it slightly wrong, it doesn't matter. Now, I've also brought the tool in until it's just touching the stock, and I've used my finest feeler gauge stock to locate that. And I've set my compound slide collar to 0. And according to my CAD drawings, I need to be able to advance that tool in along that flank for 129 power. Now, I usually work in metric, but my compound slide is an imperial, so I have to work with that. And I've decided to do the biggest one first. If it all goes really badly wrong, I guess I could machine it off and do something different, I'm not sure. But it just seemed to make sense to work with the one closest to the chuck face, just in case something digs in. So I've got my tailstock tight. I'm going to run it at fairly low speed and use plenty of coolant, and we'll see how the first one goes. The potential for things to go wrong here is extraordinarily high, so let's just see. We're at about 45 thou deep. Seems to be going okay, but I'm just I'm noticing that one edge is starting to gall up a little bit, which worries me. If it gets really bad, I'll lower the speed even more. Okay, that's 55 thou. I just heard it starting to dig in there. Now in theory, it's really only cutting on the square end and the left-hand flank. However, it presents a very wide cutting face to the stock, so the load on the tool tip goes up quite high as you start to cut across a broader area. And given that this lathe is old and not super rigid, the potential then is for the tool tip to dig in and deflect downwards. Now in theory, if it deflects downwards, the load on the tool tip clears and it'll spring back up again, but you tend to get this sort of oscillating effect, and that's when you get chatter and that sort of thing. So just I'm just going to lower my RPM a little bit more. We're at 85 thou, and I can hear it sort of digging in and releasing, and I'm taking this very, very slowly. Funny thing is, I did this on the original pulleys for my drill press years ago, and I don't remember having this sort of issue, and maybe I was younger and more reckless, I don't know, but this is really worrying me. Keep going, let's push ahead. It's 90 thou, bit more. That's 100 thou. So what do we got? We got still got 30 to go. Well, this is the next day, and after I finished up yesterday, I tried cutting that second groove and nearly ruined the whole thing. The tool bit was digging in constantly, and I was at a complete loss. I had no idea why this was happening. I had everything locked down, everything was tight. I had the tool honed and sharpened, I checked the center height, but it was grabbing and digging in, and I was terrified it was going to snap off or disrupt the part. So I packed up and slept on it, and today what I have done is I've cut all of the groove positions with the parting tool first. So I've already done these three here with the V tool. These three are the last three to be done. So with the parting tool, I've got an inverted parting tool holder, and I ground a blade that was very thin. It's just over 1 millimeter thick, I index the correct position of this shoulder here and cut each of those 3 grooves to the correct depth. And what that does is it sort of provides, or at least removes, the bulk of the material. So then the V-tool only has to form the shoulders of the V groove. And I also have a pretty dodgy sort of Chinese electromagnetic coolant pump underneath my lathe here. And I also reasoned that if I was able to get a constant supply of coolant, it would not only keep the blade from expanding and jamming in the cut, but it just provides that lubricant as well. So you know what, there's no problem you can't solve with a bit of lubricant. So I'm about to do these 3 here, and if I get that done without a mishap, I'm sort of feeling a lot better about this. But as of yesterday, I was just ready to chuck this whole thing in the bin and not go any further with it. The only problem was I'd already uploaded part 1 of the video, so it would have seemed a bit strange if I didn't follow through. Incidentally, I noticed that Mr. Pete finally got his pull gear apart, and he's uploaded a video showing the interior of the pull gear. And as I suspected, I don't know how he's getting a 7:1 ratio with that set of gears that he has. So I'll have to pause the video and do a tooth count, but I'm pretty sure it's not going to be 7:1. There was a version that came out with a 7:1 ratio, and from the information I can find, it had a double reduction in the planet gears. The one that he has doesn't have that. So hopefully Mr. Pete's going to shed some more light on that soon. So let's go ahead and get these 3 grooves finished, and we're looking sweet. So here we go. Alright, that went okay. So I just keep indexing across now the distance between each V groove, and we'll go from there. So what you should be able to see now is that the 3 beads on the back of that poly V belt fit into those 3 grooves, and you get quite a large surface area as it wraps around those 3 indentations. And because the belt is very thin in section, it wraps around really well around that smaller diameter. So you do get a very positive drive, and it runs very quiet and very cool, and it's very efficient. You don't get a lot of friction to sap energy from the drive. So what I need to do now is take this out, flip it around, and start machining out the inside of this casting section, and that's where the idler gears are going to fit. So I'm very glad to have that finished. That was a bit of a nightmare, and I could see that I was very close to snatching defeat from the jaws of victory there. Okay, progress report as I close out this video. I think I've sort of done enough to fill up 35 minutes. What I got done today was I machined this 8mm wide slot in the top of the cap casting. This allows for a latch to be dropped into that slot, and that locks the center spindle to the top cap. That effectively gives you a 1-to-1 drive with the pull gear. If you want to engage the low speed drive, you need to lift that latch out and rotate it through 90 degrees, and then it holds in a position above the top cap. That allows the center spindle to rotate independently of the step pulley section. Now, when you want to engage the low speed drive, what you need to do is to lock this top cap into position so it cannot rotate. To do that, there's a 3/8 diameter drilled hole in the edge of this casting, and a steel rod will be inserted in that, and that steel rod is locked to the body of the drill press. So there's a 2-step process to engage the low speed. You need to lift the latch out and insert that steel rod to lock the cap in position. So the cap is more or less finished. The bearing recess for the top of the spindle is done. The one remaining job to be done here is to drill 4 holes in the underside of this cap for the spindles, which are going to hold the idler gears in place. So these spindles have been machined from stainless steel. It was probably a poor choice because it was extremely hard to machine and cut the threads and all that sort of stuff. It was just very tough stainless. And I thought long and hard about how I was going to fit these spindles into this cap, and I thought about press fitting them and using Loctite. And in the end I decided to cut very fine thread. That's a 5/16 by 40 TPI model engineer thread. It's undercut at the shoulder, so it will screw down all the way to the shoulder. The length of the stud is 0.1 of a millimeter more than the thickness of the gear, so that when that's screwed down hard, the gear will just sort of rotate just clear of the cap. And I also thought about how I was going to get some torque on this to actually hold that in place as well. And in the end I decided to drill a cross hole, and I can use a steel rod or a pin punch or something. Here we are. So I can put a pin punch through there and use that to get some torque on that stud and hold it in place. Now it also meant that I could have a through hole which connects up with that cross hole. And I had one of those sort of moments of clarity, I suppose you could say, when I thought, well, you know, I could use this to lubricate the bronze bushes, the sintered bronze bushes in the center of the gears. So the idea is going to be that when I have drilled through and threaded for each one of those studs, I'll continue the drilled hole all the way through to the other side of the cap. And I'm going to fit some of those little brass ball oilers in the cap. So there'll be 4 of them, 1 for each stud, and they'll be, because they're spring-loaded ball ends on them, I can inject oil through those studs and they'll close up and stop dust and debris from getting into the bushes. So I thought, oh, that's cool. That's something that the original manufacturers didn't think of. They actually fitted 2 bronze or 2 brass oilers in there, but I think they just sort of splashed oil on the gears. So this is going to be one of those really cool features that will stop those little sintered bronze bushes from running dry, if you remember to oil it. So each one of those little studs is done. There's a bronze washer on the top, and it's going to just prevent the gear from coming off the stud when it's inverted. So remember, all of this is sort of upside down when it's in operation. Now the location for each one of those holes I'm going to take from the CAD drawing. I've drawn this out, so I've got 0.1 millimeter clearance or backlash for each of the gear sets, and I intend to drill this on the CNC mill. Now it's a high risk strategy, so I'm not going to do it in this part until I've tried it out on a piece of scrap material, and if I'm happy with that, I'll go ahead and drill each one of those holes. So yeah, the cap's done except for those 4 holes and fitting the oilers, which I've ordered and they're on the way. Now this was the part that gave me the most grief, and I think I've got away with it this time. So here's my stepped pulley. It's now held in place with 6 M5 countersunk screws, and I've Loctited this as well so that it's essentially one component now. Bearing recess is cut. The clearance for the main spindle has been cut, and that's all going to assemble in there like that later on when the bearing is pressed home. Second bearing at the top in this recess here, which is still to be machined, and the gear, the drive gear, will fit in place like so. So that's sort of like 80% done as well. The spindle has a plunger on the inside. Now this part is going to be protruding from the top of the spindle, and there'll be an 8mm wide steel latch assembled onto that, and that's what's going to lock or unlock the drive. So that's just a bit of mild steel and just a bit of a spring that I had lying around. So that's looking good. So is it going to work? Don't know. I sort of have ambitions that are a bit beyond my skill level sometimes. I'm keen to see how it winds up, and I do really need some sort of reduction drive on my drill press. It just doesn't have the power that I need to run large diameter drill bits, so we'll see how we go. So I'll leave this here now. I think my explanations are a bit long-winded sometimes, but hey, if you want to be entertained, go and watch this old time. So for now, we'll wind up here. The next episode you see, hopefully we get this sort of at a stage where we can tell whether it's going to run or not. Thank you to the people who have left comments. It does give me some encouragement to move forward with this. I've noticed that Mr. Pete has been watching my videos, which is cool. I really like it. There's somebody well known is actually looking at what I'm doing, or maybe he's just checking up on me because I mentioned his name in the title. Who knows? But yeah, exciting times. So for now, thanks for watching.